the basic topology that covers the countable and uncountable sets. So first we are going to recall some notations. So first one is the set of natural numbers that is denoted by n, and it is containing the numbers from 1, 2, 3, 4, 5 up to infinity. Then is the set of integers which is denoted by z, and it is the set containing the positive natural numbers, so on, and also the negative numbers, so on, including 0, right? Then is the set of the rational numbers that is denoted by q, and it is the set of the kind p divided by q such that p and q are belonging to the integers where q is non-zero, right? Then r is the set of real numbers, and if I exclude the rational numbers from the real numbers, then I will be getting this to be as the set of irrational numbers that is denoted by I. And then C is the set of the complex numbers. So we can also understand this diagrammatically. Here C is the set of the complex numbers and R is the set of the real numbers. Q is the set of the rational numbers. If I exclude the set of the rational numbers from the real numbers, then I'm getting this set to be as a set of irrational numbers, right? So we can write that the set of natural numbers is a subset of the set of integers, and the set of integers is a subset of the set of rational numbers, and the set of rational numbers or irrational numbers is a subset of the set of the real numbers, and set of the real numbers is further the subset of the set of the complex numbers. So the set of complex numbers is the biggest set, right? Okay. So now let's move on to the definitions of functions or mappings. So if I define a rule f from the set x to the set y in such a way that every element of x is associated with a unique element in y. Suppose x1 is associated with y1, x2 is associated with y2, x3 is associated with y3, x4 is associated with y2, x5 is associated with y4. So these y1, y2, y3, y4, these are the images of the elements belonging to x, right, to which these are associated. So here, what is y1? It is the image of x1. y2 is the image of x2 and x4. y3 is an image of x3 and y4 is an image of x5, right? So here every element of x is having one and only one image in y. Different elements of x may have the same image in y. In this case, x2 and x4, these two are having the same image in y, that is y2, right? But an element of x cannot have more than one image in y. If y1, y2, y3, y4 are called the images of elements of x under F, then what is x1, x2, x3, x4, x5 are called? These are called the pre-images of elements of y under the function f, right? So here y1 is image of x1 under f, right? We can also write this as f image of x1, or you can also write this as f of x1, the f image of x1. Similarly, we can write y2 to be as the f image of x2. And also y2 is the f image of x4, both x2 and x4. So we write y2 to be equal to f of x2 equal to f of x4, right? And y3 is f of x3, y4 is f of x5. Here x is called the domain of f and y is called the codomain of f, right? There is one more term, the range of f. What is the range of f? Range of f is the collection of all the elements of y which are associated with the elements of x, right? So here the elements of the range consist of y1, y2, y3, y4. This is the range of f, right? So from here we can also say that the range of f is a subset of codomain. So here x is called the domain of f and y is called the codomain of f, and the range of f is, it consists of all the images of elements of x. So that is y1, y2, y3, y4. That's it, right? We can also write this as f of x for which x is belonging to x. So this can further be written as f of x and it is also the subset of y, right? Okay. So let's read the definition of function now. So a rule f which associates every element of x with a unique element of y is called a function of x into y, where x is domain of f and y is called the codomain of f, and the range of f is all those f of x for which x is belonging to x, and that is equal to f of x which is a subset of y, right? Okay. The another definition, if we define the function f on x to y by f of x equal to y for all x belonging to x, then y is called image of x under f and x is called the pre-image of y to which it is associated under f, the function f, right? Okay. Now when a function is well defined, a function f on x to y is said to be well defined if x1 is equal to x2 implies f of x1 equal to f of x2. That means if one element of x has one and only one image in y, right? Next definition is about when the two functions are equal. Let's consider two mappings f and g. So f is a mapping from x into y and g is a mapping from x into y. So these two are equal. These are said to be equal if f of x is equal to g of x for all x belonging to x. This should happen for every x belonging to x. So when fx equal to gx, the mappings are equal. Then is one-to-one function. So a function f on x into y is said to be one-to-one function if x1 not equal to x2 implies f of x1 is also not equal to f of x2. That is, if different points of x have different images in y. This is what does it mean? If different points of x has different images in y, right? Or we can also say that if f takes different values at different points, right? Or equivalently, if f of x1 equal to f of x2 implies x1 equal to x2. Please note this is important. So the remark says f is a function from x into y is 1, 1 if and only if f of x1 equal to f of x2 implies x1 is equal to x2, right? If you write this in another form, then you have to write that x1 not equal to x2 implies f of x1 not equals to f of x2. If you start from here, you must write two different points first, and then implies the two different images. In any of the ways you can start, either from the same images or from the different points. Then is the onto function. A function f from x into y is said to be onto if every element of y has at least one pre-image in x. The points belonging to y must have at least one pre-image in x. That means all the points of y must have the pre-images in x. At least one. So let me write this. A function is said to be onto if for every y belonging to capital Y, there exist, this is a sign for there exist at least one x belonging to x such that f of x is equal to y, right? So in this case, what is your range? The complete set y, right? So here, the range of f is equal to y, right? Because all the elements of y is having at least one pre-image in x. This is what the difference in case of the onto function, right? Please note this remark. A 1, 1 function is also called injection. An onto function is also called surjection. And 1, 1 and onto function is also called bijection. Right? Okay. Next is when the functions are equivalent. If f is a mapping from x into y is 1, 1 and onto. If it is both 1, 1 and onto, then there is a 1-to-1 correspondence between x and y. Then we say that x and y are equivalent. And we write that x is equivalent to y, right? Next is finite and infinite set. Let me consider Jn to be the set of natural numbers from 1, 2, 3, 4 up to n, right? Where n is a positive integer. A set A is said to be finite if there is 1-to-1 correspondence between A and Jn. If either A is empty, yes, an empty set is a finite set. If either A is empty or there is a 1-to-1 correspondence between A and Jn, right? And the set which is not finite is called an infinite set, which means the set A is infinite if there is not a 1-to-1 correspondence between A and Jn. So the set which is not finite is called infinite set. Then are the countable sets. A set A is said to be countable if there exists a mapping phi from the set of the natural numbers to A, the set A, such that phi is 1, 1. Second, phi is onto. It should be both 1, 1 and onto. Or in other words, we can say that if there is 1-to-1 correspondence between n and A, right, then A is said to be countable set. So another definition of countable set is if there is a 1-to-1 correspondence between n and A, then A is said to be countable. Now, is A is infinite or not? Is a countable set is infinite set or not? Obviously, a countable set is an infinite set. Why? Because there is a 1-to-1 correspondence of A with the set of natural numbers. And the elements of the set of natural numbers are infinite in number, right? So every countable set is an infinite set. And the set which is not countable is uncountable. Please note this remark. Every countable set is an infinite set. And the set which is not countable is an uncountable set. Let's define f function from n to a, where n is a set of natural numbers, and I'm defining this by f of n equal to xn for all n belonging to the set of the natural numbers. Then the set xn, which is x1, x2, x3 up to so on, right? This is a sequence. That is what I have done, that I have arranged the elements of A in a sequence. If we are able to arrange the elements of A in a sequence, then we say that A is countable, right? So thus, A is countable if and only if A is equal to x1, x2, x3 up to so on, the set, right? In other words, A is countable if and only if all the terms of A can be arranged in a sequence. In a sequence xn, right? And then the last definition is on the at most countable set. At most countable set, either it is finite or countable. So a set which is either finite or countable is said to be at most countable. So here these are the remarks which are very important. Please note this. If f is a mapping from A to n and if it is 1, 1, then A is at most countable. If f is a mapping from set of natural numbers to A, and if this is onto, then A is at most countable. If f is a mapping from the set of natural numbers to A is onto and A is infinite, then A is countable. And if f is a mapping from a set A to the set of natural numbers is 1, 1 and A is infinite, then A is countable. So these are the mappings that describes when the set A is at most countable and when it is countable, right? So this is a quick description about the sets. The sets which can be infinite sets or finite sets, and infinite sets can be countable sets or uncountable sets. Countable sets, the sets which are having one-to-one correspondence with the set of the natural numbers, and uncountable sets, the sets which are not countable, right? Thank you.